Okay, the next speaker, substitute. This is Dr. Maxim Dukas, who's speaking for the G1O, and he will talk to us about the multi-scale model.
Thank you, and I would like to thank the organizers of the meeting for selecting our abstract for presentation. I also have no conflict of interest to disclose. So I'd like to go back to the realm of mouse hair biology. And I want to point out, since there are thousands of hair follicles in mouse skin, day regeneration is a group behavior, and as it proceeds, it generates very striking patterns of hair regeneration that could be visualized upon shaving of the animals, and I'm sure many of you are familiar with it. One of the key features of this pattern is the asymmetry, as visualized here in adult and aging mice. But I also would like to mention that prior to the onset of full asymmetry of the patterns, mice undergo through a lengthy phase of bilateral symmetry, shown here at the bottom in young mice. And with everything that we understand about the patterning process, which essentially relies on rare stochastic hair cycle activation events, coupled with hair cycle spreading through hair-to-hair coupling, we cannot really explain bilateral pattern formation. So to address this phenomenon of bilateral pattern symmetry, we've resorted to a computational model, and we were able to run a lot of mathematical simulations to find the conditions that are compatible with bilateral symmetry. And as shown in one of these mathematical simulations with green bean anagen and red bean telogen, any type of parameter sets under the key assumption that all hair follicles are equal will not generate bilateral symmetry. And the only conditions that are compatible with bilateral symmetry are demonstrated here. So the key new assumption that is required for this is that when there's an interaction between two distinct skin domains where hair follicles have distinct hair cycle parameters. So this is quite conceivable because in addition to the dorsal skin of the mouse, you would all agree there are other anatomical areas, including prominently ventral skin, cranial domain, chin skin, as well as limbs. So when we modeled a condition of the two-domain interaction representing the dorsal and ventral, we can very easily obtain bilateral pattern symmetry already in the second cycle. So what is shown on the right are the snapshots of the computational simulations, and I will simplify it by removing ventral domains. So now what you're looking at is essentially a computer mouse with green bean anagen, and you can see that already in the second simulated cycle you obtain bilateral symmetry, and it's maintained through the next two cycles. What we did next is that we went back to mice and looked for the proof of ventral dorsal hair follicle interactions. And the approach that we took is by using whole skin flash reporter mouse. So this mouse model was developed by Kirosh from University of Queensland, and it enables in vivo imaging of the canonical wind signaling in form of luminescence, and luminescent signals could be calibrated to reliably reflect specific hair cycle stages. So compared to conventional hair cycle observations through pigment changes, this is much more sensitive, and it can pick up the earliest onset of anagen. And what is shown here is a representative mouse tracked over the course of almost 50 days. And I just want to point your attention to two time points, postnatal day 24 and 44, which represent the onset of second and third hair cycle. So you can appreciate here, and what you're looking at is dorsal and ventral skin of the same mouse, that second and third hair cycle initiate ventral. On the ventral side, and then if you visually track the next day, you will see that they spread onto the dorsum through the flanks of the animals, generating bilateral symmetry. So we went on to validate that by a more conventional approach, so we essentially skinned the entire mouse and carefully analyzed the hair distribution patterns. Based on that, we produced this Jamaican flag-like maps of mouse skin, and here you can appreciate that during the onset of second anagen, there's ventral to dorsal hair spreading, which goes on to produce visually bilaterally symmetric dorsal patterns. Now, on the next slide, what I will show is actually a composite temporospatial output of flash reporter mouse luminescence, which clearly demonstrates here that there's ventral dorsal phase shift in hair cycle initiation, and it's easy to see with blue color. So essentially ventral hair cycle during second, third, and fourth postnatal hair cycle starts first ventrally and then spreads dorsally. So with that in mind, we were wondering if in adult animals, when full asynchrony develops in the dorsal skin, are there conditions that are compatible with the maintenance of bilateral pattern? So to our surprise, we found that prominently in rabbits, as well as in female but not male mice, adult mice, there's a maintenance of bilateral pattern symmetry on the ventral side. And we were quick to notice that this maintenance seemed to be strongly associated with hair cycle initiation at the locations of the nipples, which male mice lack developmentally. So you can appreciate this by visually tracking hair cycles around a rabbit nipple over the course of almost 80 days. So over this time period, you can you see that hair cycles initiate at the nipple location and then propagates outwardly, generating circles that later merge into lines on the flanks of the animals. Similarly, in female mice, you often will find specific hair cycle initiation at nipple locations. And we also correlated this positively with early acquisition of telogen competence, so the phase when BMP activity is downregulated, as shown here using LAC-Z reporter for BMP signaling. So at the 2 to 3 hair follicle distances around the nipple, there's early acquisition of competence and loss of BMP activity within the bulges of the telogen follicles. So what we did next is that we performed additional luminescence reporter assays on female mice this time and compared them to males. So you can appreciate here that unlike males shown in the bottom, females have bilateral and nipple-centric initiation of canonical bioluminescence activity, which is reflective of the hair cycle initiation events. And on the next slide, we see a composite temporospatial map of the nipple locations, and very clearly females but not the compatible sites on the male mouse skin have nipple peaks reflective of the hair cycle initiation events. Now, to prove this further, we turned our attention to an interesting mouse model that was developed decades ago by John Wysłomirski. So this is a K14 PTHRP mouse where during development ventral skin undergoes transformation into a nipple-like field. So if our assumptions are right, what we expect in this mice is that dominant hair cycle initiation from the bunches with this nipple-like skin. And this is indeed what we see. So you can see that hair cycle patterns in this mice actually convert into tidal waves propagating from the bunches of the nipple-like skin. And this tidal wave patterning is enforced essentially throughout the lifetime of these animals, and even animals as old as almost 1 year, they are still maintained. At this time, wild-type mouse would be expected to have complete breakdown of symmetry. So we also grafted the skin, and we grafted nipples from rabbits onto the dorsal skin of post-skid mice, and what we see is that the grafts now become dominant hair cycle initiation sites. So what we are doing now is trying to understand the cellular and cycling basis of the hair cycle inductive activity of the nipples, and to that end we've collaborated with John Foley from Indiana University, and right now we have microarray data from sorted fibroblasts and keratinocytes from the K15 PTHRP nipple skin, and we see a lot of differences in both cell populations comparing to the normal ventral skin, but strikingly, specifically in nipple-like fibroblasts, there is an enrichment for a variety of growth factors, and many of them, some of them are shown at the bottom, many of them already have an attributed antigen initiation effect. So, like for example, FGF10, 7 ligands, ligands of the PDGF signaling pathway, IGF, as well as inflammatory cytokines. So the ongoing work in the laboratory is now focused on trying to further elucidate the signaling mechanism behind the nipple activity and hair cycle initiation. And with that, I would like to end and acknowledge specifically Ji-Wen Oh, who is a postdoctoral fellow who performed most of the work, as well as my collaborators, the mathematicians at UCI, Kirash from University of Queensland on his help with flash reporter mouse, and John Foley on the nipple experiments. And I would like to acknowledge my funding sources. Thank you.